Okay, can everybody hear me well? So thanks for coming, guys. I don't know how this lecture is going to go. I still have serious problems in coming at really realizing what has happened. And I guess that applies to many of you, or basically all of you. And in particular, since being at the university is, for many of us, perhaps the best time in our lives. To me, that was when I made my deep friendships, when I could actually just spend time getting new insights, new knowledge, and all the nice things which happen. And this should be a place where you don't need to be afraid. So I hope we can keep this atmosphere which we've been having for the rest of the semester. I mean, it's been a great, great pleasure to get to know all of you. I think you're fantastic people, and I see that for the way you've been acting today, been behaving here. And I hope we can gradually come back to a kind of normal situation. And you've probably seen from the weekly plan which we put up, this is just a suggestion from my side. And I wanted to bring up some of the things which were in this homework 5, because they also link with the midterm. Now, the midterm, we roughly have close to 2 weeks for it. So, and I try to reduce a little bit the amount. I don't know if I did it right or not. It's up to you to see. And please feel free to come with input and tell me whether you think we're doing too much or too little. I was thinking that also next week we can use Wednesday and Friday to discuss the solution of the midterm. And we are going to obviously have Friday this week where we discuss the midterm as usual. And then the lectures which you will see, which we're going to have today partly, and also Wednesday and next Monday, they will all be linked with the kind of stuff which we need to solve the midterm. So hopefully we can get back in a kind of, yeah, I don't know if whether I should call it a normal situation. I still have problems in realizing what has happened. And I just want to see how this lecture evolves. Yeah, let's see what happens. And just move slowly and just try to take care of each other. So I wanted to say a little bit about the discussion which we had in this homework, because there are things which are related to the way we solve the midterm. And in particular, in many of the exercises we've had till now, we have been using Euler's method. And we mentioned loosely that Euler's method does not conserve energy. And we are going to look at why and how we can, in a very, very simple way, get an algorithm which conserves energy. And you will see this also in the midterm, that we are going to look at a kind of harmonic oscillator system. And that system, if we use Euler's method, as time moves on, is not going to conserve energy. So for those of you who are interested in this kind of topics, there's actually a lot of mathematics on the solution of differential equations on energy conserving systems. And these are called, they have a class of ordinary differential equations, which are called symplectic differential equations. And there you can actually show that there are specific algorithms which conserve energy. Any questions before we slowly move on here? Things which are unclear, things you would like to bring up. I mean, we all have lots of feelings and emotions which are perhaps not so easy to tackle. But so if there are things you would like to bring up, I mean, feel free to do that at any time. And also, when it comes to the deadline, you Normally we tended to be a little bit pickier with the deadlines on the midterms, but clearly this situation here is not normal. So we put a deadline for your planning, the end of next week. I don't like to have things which linger into spring break, but in case something goes wrong and you need more time, there is no problem with that either. So I hope you don't get the feeling that we are rushing on. We just need to take a little bit of time and see how things evolve, right? And I need myself to see if I'm able to hold this lecture. Okay, the other thing is also that everything will be as before. I mean, the lectures are recorded. We try to keep this kind of hybrid mode, if that's okay with everybody. So you can always revisit the videos and look back at what we've done. So what I wanted to do now is to bring a little bit up the parts of the things last week, which were linked with this homework number 5. Now you found probably the solution to homework number 5, so you can look into it. But I wanted to emphasize some of the topics here and then bring that back to the solution of differential equations. So this lecture today is a little bit more of the type hands-on with numerical methods. But there is physics, because we can actually test whether what we've been talking about in connection with energy conserving forces, that actually takes place. But when we solve things numerically, we always have to be careful, because a numerical method is an approximation to what we do. Which means, for instance, that there is a specific algorithm. There are parameters like this step size in time, which we need to set and understand a little bit deeper. And these are things which may sometimes make us not see the wood for the trees, because there are suddenly many different things which come simultaneously. I mean, we have to test the physics, and then there is also a numerical and mathematical element. So today I just wanted to focus a little bit more on the numerical elements. And we are going to bring in some of these now and then. Later, we are also going to see how we can write more systematic code, where we can actually bring together many methods and use the methods which are relevant for the type of physics. So what you're going to see today is okay if we are looking at energy conserving systems. But if you're looking at systems where we don't conserve energies, like a pendulum which has some damping, then one of the methods which we are going to study today, which is extremely popular in simulations of big materials, in material science, is called molecular dynamics. That method there is not the best one if you are looking at systems which dissipate energy. So the methods have all their pros and cons, and it's us as physicists and scientists to be aware of what works and what does not work. And that depends always on the physics of the problem. So in this case, we are going to look at the system which is energy conserving, and that was the Earth-Sun case. Now, in the exercise which we had, so I'm just scrolling down a little bit, and we are coming back to this when we, in the second midterm, we are actually going to simulate the solar system. And we will begin in the second midterm with what you see here. So just keep this example in mind. And we are going to, I mean, last year I actually asked your fellow students whether we should do the solar system or not. And there was a popular vote. I mean, 100% everybody wanted to do the solar system. And that's a pretty cute thing to do. And you can actually do it here. And we're going to start with the Sun-Earth system. And as you can see, the force is the one you have here. It's a gravitational force. And one of the things you end up doing first is actually to rewrite the equations as coupled differential equations. And we discussed this a little bit earlier in the semester we actually saw that when we introduced x is equal to the radius times cosine theta, we could have the x component of the force and the y component. And this is a two-dimensional case. There's nothing which hinders you to set up the three-dimensional case. And then we could rewrite the forces in terms of an x component and a y component. And this r is x squared plus y squared. And if you think back to the homework we had with a falling object and with an air resistance, which went like the velocity squared, then we could not decouple the two differential equations. And we could not find an analytical solution if we insisted on a Cartesian system. Now, after spring break, we're actually going to solve these equations analytically. This is a set of equations which can be solved analytically. And that's extremely useful because it allows us to get a little bit deeper insight about the way we model as celestial objects like the Earth and the Sun, etc. So, but that's something which we're going to deal with after spring break. So the equations which we end up having to solve, and I'm just going through the slides here a little bit, is the equation for the velocity in the x direction, the position in the x direction, the velocity in the y direction, and similarly a position in the y direction, which now the derivative here gives us the velocity. Now, when you build a code, and this is a small technicality, you can keep the physical constants, or you can scale them away, because when you deal with a solar system, it's useful to introduce number of years as a unit of time and astronomical units as a unit for length, which is a distance between the Earth and the Sun. And in order to scale this away, you can use the centripetal force and acceleration. And then you don't know that if you have an object which goes in circle around another one, then the force here, which is given by the gravitational force, is proportional to the velocity squared times the mass divided by the distance between the Earth and the Sun. And that allows you to simply say that this g times the mass of the Sun is equal to the velocity of the Earth times the distance between the Earth and the Sun. And then we know that the velocity is equal to the distance the Earth travels in a year. And if you assume that this is a circular orbit, then it's 2 pi times r, that's the distance. And you divide with a year, and then you get 2 pi times 1 astronomical unit, which is the distance to the Sun, divided by a year. And then you can scale away constants. Because sometimes it's less convenient to actually deal with all the physical constants. So this is a kind of scaling of the equations, which we discussed in the beginning of the semester. The discretized version, when we now look at Euler's method, is now given by the updated velocity in the x direction, the updated position in the x direction, and the same in the y direction here. And these are the equations which we're going to plug in. And if we now implement Euler's method, which is very simple to implement, so we have the acceleration here. So this is this constant 4 pi squared times the distance divided by the absolute value, the distance cubed. So this is our acceleration. And I told you that we are basically just going to make small changes to the codes which we have developed in the previous homeworks. So when you come to the midterm, you can reuse what you see here, but just change the accelerations, find new forces. And you can do the same when it comes to the second midterm, when we are going to deal with the buildup of a code for the solar system. So basically what you see here is not going to change that much. But if you run this now, and you see in these units, I have 10 years, and I have a time step, which is 10 to the minus 2 here, now 10 to the minus 3, as you can see. So these are parameters in our approximations. So if I run the code, you will see something which is not, this doesn't look well. So what you see here is the X and the Y position of the Earth with the Sun at the center. And if you think of X along one axis and y along the other one, this simply means that the orbit of the Earth is not stable. So if I let this run for many more years, this is actually going to just worsen, and suddenly the Earth is going to leave its orbit. You will also see that energy is not conserved here. So this is Euler's method. And there is another method which is called Euler-Chroma, which simply means that we can just make one change in our codes. And I'm coming back to that on the whiteboard. So in this change, we simply use the new velocity here. And if I do that, wow, it looks like this. And suddenly it's stable. If I use this algorithm, it's just a small change. If I use this algorithm, it's also going to conserve energy, as you will see in just some few moments here. So Euler's method, the way we normally use it, and which you probably have seen many, many times, is just a Taylor approximation around a point. And then you can find the updated solution in terms of that, is a method which, one, doesn't give us proper orbits. I can actually make this delta t smaller and smaller, but then the code is going to get more and more inefficient. And it will, at a certain point, it will break down anyway. So Euler's method is very useful to get a kind of a back of the envelope estimate, but normally it fails miserably, especially if you want to conserve energy. And you can see that in the in a code below here. And we are coming back to why this happens when we now look at the whiteboard. But let me bring up another method, which is actually called velocity relief. And I'm going to derive that one. This method is a method which is even more stable than Euler-Chroma. And you see here now the orbits are pretty nice. And I can also look at energy conservation here. And in this particular case, what I've done is now to define the kinetic energy, the initial one, and the initial potential energy. And later here, when I have updated the velocity, I do the velocity squared, and I have my potential energy, which is this 4 pi squared divided by the absolute distance between the Earth and the Sun. And if I plot that, what you're going to get now, you have to look at the top of the graph. So at the top of the graph, you see it says minus 19.7 something times 10 to the minus 9 multiplied with the values you see in the graph. So these oscillations are oscillations at the level of 10 to the minus 9. And you see another thing is that they oscillate between a min and max values, but they never explode. So that means that the orbit and the energies and everything will stay stable as long as we run the computations. Now, your results will always depend on delta t. So if I make this delta t smaller, then that error in energy is going to drop to even smaller values. If I make delta t larger, you will have to live with a larger error. But these are methods which basically conserve energy. So what I want to do the rest of the day now is actually to talk a little bit about these methods, because you will need them in the next midterm. Now, the simplest thing, if you don't want to dive into this velocity Valais method, which is a standard, it's actually an industry standard. If you do material science, it's very simple to implement, and all these methods are based on Taylor expansions. It's just manipulations of Taylor expansions. Essentially, all famous numerical algorithms for solving differential equations are based on that. So there's nothing, how to say, deeper mathematically than that. Then you can obviously look at the stability and convergence of the methods, but the basic derivations are pretty straightforward. Just manipulate Taylor expansions. So let's take a look at it. And at the same time, when you have this code here, you could actually have calculated the angular momentum and tested whether angular momentum changes. So if you were to calculate angular momentum here, how would you calculate angular momentum? So you're updating position and velocity. And if you now want to find the angular momentum as a function of time, what would you do then? Yeah? Exactly. So you find, when you solve the equations, you find the velocity and you find the position, and you just take the cross product of these vectors. And then you have the angular momentum. And then you can plot the angular momentum as a function of time and see if that is conserved. So that means that with a code like this one, you can test a lot of the physics and see if what we have been talking about actually makes sense or not. Now, the thing we always have to be careful about is whether the methods we have chosen to solve are useful and meaningful. So let's take a look at these numerical methods before we go back to more theory, which we will take up again on Wednesday. So let me just bring up this and let me know if you have any questions to what we have here. I just wanted to bring up this. So let's look at these methods. So when we looked at Euler's method, so this is just our numerical part now. So we have Euler's method. And let me quickly remind you of how we actually developed that. So if you think of a differential equation where you have a derivative of dt, and this is equal to, not df, but this could be dx as a function of time, and then we have an expression here where it depends on x and t. So typically what we do now is that we discretize, we let time go over to a discretized time, and x goes over to a discretized position x. And then we make a Taylor expansion in the same way as we did last week. And so we would expand x around the time t plus delta t, which we then, when we looked at this discretized version, this goes over to x of t of I plus delta t. And we would typically write this now as x of I plus 1. So plus 1 because we make one time step. And this is going to be given by x of t of I, which we are going to rewrite as x of I. And then we have the term delta t, and now we have the derivative, which is x prime here at the time t of I. And then we have higher derivatives, which are just right like O of delta t squared. And Euler's method, when we look at that one, that means that we simply now replace that with the first derivative and a term which goes like delta x. So in Euler's method, then we have x of I plus 1, which is now approximated. So I'm not putting in an approximation sign. So this is given now by delta t, and then it has x derivative at time t of I. And this is the same as, so this x prime at dx dt at time equal to t of I. This is nothing but the velocity of v of I. And that means that what we have is x of I plus 1, which is equal to x of I plus delta t times v of I. And then we can do the same thing with the velocity. And this is actually what we started solving in the beginning of the semester. So we get plus delta t, and then we have the time derivative of velocity, which is the acceleration. And these are the typical equations which we've been solving. Now, in Euler-Kromer's method, what we would do then, so you see now that you have a truncation, which goes like O at the level of delta t squared. So the arrow which we have goes like delta t squared. So Euler-Kromer, on the other hand, what that actually does is that it calculates v of I plus 1, and this is given by v of I, as before, of delta t of a of I. So it means that it stops truncating at delta t squared. So we keep only terms up to delta t, but then we change x of I plus 1 to be x of I plus delta t. And now the velocity is given by this v of I plus 1. So which means that I have a v of I plus delta t times a of I. And this term, which you see here, is actually v of I plus 1. And in this case, we have a term which goes like delta t squared. So that means that we make an approximation which is asymmetric in time for position and velocity. So here we have left out terms which go like delta t cubed. So that means that if you are interested in a better position, then Euler-Kromer's method does that. However, the velocity will still be approximated in the same way as we implement Euler's method. So the velocity will be, the error there will be asymmetric compared with the position. Now, this method is actually a method which conserves energy. Now, how many of you have taken linear algebra? Okay, there's some of you have done that. So these equations which you see here, they can actually be rewritten like a matrix times a vector. Now, in order to conserve energy, something which is called the determinant has to be independent of delta t. And you will see now, and I'm going to sketch this for you. So to see the full proof, you would actually have to take in a more advanced course in linear algebra. But I wanted to show you the general trend, how you can actually study an algorithm like this one, Euler-Kromer and Euler's method, and get a feeling of why one of them is going to fail and the other not. So this is a very loose sketch, but let me just write this down. I know that this is something which not everybody has seen, and I hope you can forgive me for that. But if you now look at the expressions here, we can rewrite, if we look at Euler's method, we can rewrite this in a more compact way, where we have a vector with the new positions, x of I plus 1, and v of x of I plus 1. So this is supposed to be a number 1. And we can rewrite this as a matrix. And if we now go back to Euler's method, you will now see that it has x of I, the previous value here, which is just given by, this would be 1. So if I put now x of I here, and v of I here, this is a vector, and this vector gets transformed. And you will see now that when I multiply with the v of I, I'm multiplying with a delta t. So I have a delta t here. And then when I look at the velocity, so the velocity here has now a term which goes like v of I. And now we have to be a little bit careful because we would have 1 here. And now we have a term which goes like the acceleration, a of I, times a delta t here. Now, one thing we can do as an example is to look at an harmonic oscillator, which we discussed last week. So this is the harmonic oscillator. So this is not something which we are going to dive too much into, but if we look at the harmonic oscillator, we have a second derivative of x, of d of t, which is given by a term which goes like minus an omega squared multiplied with x of t. And this omega squared is actually given by the constant in the harmonic oscillator force divided by the mass. So this is normally called a natural frequency, and we are coming back to this. So we can then rewrite everything as two coupled differential equations where dx is equal dx dt is v of x, and where we have now that dv of x, the acceleration, is given by this minus omega squared times x. So if I go back to the equations now, so back to this specific equation and we plug in the terms which we have for the derivative of the velocity and the derivative of position, we can rewrite this in the following way. So we would then have a matrix, and I apologize to those of you who are not too familiar with matrices and vectors. So minus omega squared of delta t of 1. So this is a matrix which has components which are then multiplied with a vector. So we have a transformation here from a vector which contains xi and v of I. So you can actually view this matrix here, which is multiplied with a vector, as a mapping from this vector to this vector. So if you think in terms of a linear algebra, this is a mapping from one state to another state. But now we have two components. Now, in order to conserve energy, and you can show that, so in order to conserve energy, the determinant of that matrix which we have, and we are going to call this matrix for a matrix A, so that is this quantity here, then the determinant of A should be constant. So the area of this matrix here, this 2 by 2 matrix, spans an area which is given by the column vectors of that matrix. So if I calculate this determinant here, what you're going to see then is that determinant of that specific matrix is now going to be, we write it like a determinant of A, and that's going to be given by 1. So we are multiplying these two terms, and then we subtract these two terms here. So that's going to be given by something which now depends on this omega, which is given by the specific model, but we have a delta t squared. So there is an explicit dependence, delta t dependence, and this is the one which is going to cause problems with Euler's methods. So depending on different delta t values, this means that this area, which is spanned by this specific transformation matrix, is going to change as a function of delta t. So the root of the instability of Euler's method resides in this determinant of the matrix, which maps the previous positions and velocities to the new positions and velocities. Yeah, that's a question here. Could you say again? Yeah, yes. So so that matrix spans an area, which is given by the two column vectors, and that should be a constant when you perform the operations. Whereas here, it will depend on delta t. So this is only a glimpse of the whole proof. If you now take Euler-Kromer's method, that matrix changes, and you will then see that the area is constant. So let me show you that. And then we are going to stop there, because this goes a little bit well beyond on the kind of basic proofs which we need in this course. But this is more to give you a feeling of what we may have. So if you take the Euler-Kromer method, then what we have is an x of I plus 1, which now is given by this x of I, the previous value. But now we are plugging in the new velocity. So what we get then is plus, and then we have, for this specific model, we have a v of I, and then minus w squared, w0, x of I multiplied with delta t, and this gets multiplied with delta t. So we have a delta t squared term, which gives a better approximation in terms of delta t for the position, but not for the velocity. So the velocity is then given by v of I plus this delta t times the acceleration, which in this case is just omega 0 squared multiplied with x of I. And if I then rewrite this as a vector and matrix, what I have then is x of I plus 1 and v of I plus 1. This is the vector which is being transformed. And now the matrix which performs this operation for us is going to be given by 1 minus w squared delta t And this is delta t squared. And then I have a delta t here. And then I have a minus omega squared delta t of 1. And this multiplies with the original vector x of I, or the original solutions, or the previous ones. So you can look at these operations here. So this term here gets multiplied with this one. And then I add this term multiplied with that one. This is essentially the matrix where I have a row here, which multiplies with a vector. And then the next one is this row, which multiplies with that one. So forgive me for those of you who have not taken a course in linear algebra. So I hope you can forgive me. But now if you calculate the determinant of this new matrix here, let's call it A again. So this determinant of that matrix is now given by this matrix element multiplied with that one, minus the product of this one times that one. And now you see that this one has 1 minus omega 0 squared of delta t squared. And then it has, this is multiplied with 1. And then I get plus omega squared of delta t squared. And if I add these two, this is equal to a constant 1, which does not depend on the time step delta t. So that means that when I perform these transformations at every time step, this is just conserved. It has an error which is conserved and is equal to 1 for every time step. Every time I move it, if I now go to x sub I plus 2 and v of I plus 2, this matrix will have an error which is conserved. The previous one did not. And that tells you why Euler's simple method is not going to conserve energy. So this is an element of the proof. So I know that this is something which many of you have not seen and probably will not touch upon before you go into more advanced courses in mathematics. But this is just to give you a feeling of what these two methods are doing. So just this simple change, an extremely simple change, is going to give us an algorithm which is stable for basically all the purposes or the kind of topics which we are going to discuss here. So when you're coming to more advanced problems like the solar system, feel free to just use Euler-Kromer's method. That conserves energy. Now, what I wanted to give you now is just a new Taylor expansion. And that leads to a method which is called the velocity valet. And that method is an industry standard if you do material science. So in material science, you're dealing with equations which are called molecular dynamics, which are coupled Newtonian equations for billions of molecules and atoms and so on in order to simulate materials. And this method, you will be surprised, is just a simple manipulation of Taylor expansions. And that is a method which strikes a balance between accuracy and the number of CPU cycles you're willing to spend. And it is an industry standard, and it's so simple to implement. So let me give it to you, because I think this is something which is going to give you a bag of tools which you can apply to many problems in physics, also in later stages, especially if you have energy conserving problems, which we often encounter in this class. If you don't have energy conserving problems, then we may think of other methods, which we're coming back to. So I hope you can also forgive me this kind of numerical digression. But when we solve things, we often have to think a little bit deeper about the approximations which we're making. So if you now think of Euler's method, where we stopped at the first derivative, this method, which is called the velocity valet, is a method where we stop at the second derivative. So we have a new Taylor expansion now. So we take the x of t plus delta t, which we have rewritten in a discretized form as x of I plus 1. And this is given now by x of I. And then we have the first derivative. And this is where we stopped with Euler's method. So I'm just going to write this as x t of I. So this is the first derivative. And we know that this function here is nothing but the velocity at v of I. And then we move to the second derivative. so which has a 2 factorial. And this is now the second derivative with respect to t of I. And what is the second derivative of x? Yeah, that's the acceleration, exactly. So that's the acceleration, so we can actually rewrite this as an a of I here. And we have higher order terms, so that means that the error which we now introduce goes like delta t cubed, which is pretty good. So we can rewrite this now. So we have x of I, so this x of I plus delta t times the velocity. And now we are going to put an approximation. We skip the high order terms. So this is delta t squared divided by 2, multiplied with the acceleration. And then we do the same thing with the velocity. So we have a v of I plus 1 is equal to v of I plus delta t. And then we have the derivative of that one, which is again the velocity, a of I. And then we have a higher derivative of delta t squared divided by 2 factorial. And then we have v of I second derivative, and we have the higher order terms. Now there's a problem here. We don't know that one. Because that would be the derivative, the second derivative of the velocity, which would be the derivative of the acceleration. So unless you have an expression for that one, you could plug it in. But when you don't have an expression, suppose you don't have it, what's the simplest way you could actually replace that one with? So we now need a second derivative. The first derivative of the velocity is the acceleration, right? So this would be the derivative of the acceleration. But suppose we want to evaluate it numerically. And actually the simplest thing we can implement then when we don't have any refined method, how could we approximate that second derivative? Any good idea? Yeah? Yes, you use Euler actually, even simpler. So typically you will see that many of these algorithms, when you have something you cannot evaluate properly, then you just go back to Euler's method and you use that as an approximation. I think there was another question there.
Yeah, my question was about like the third derivative.
Yeah, so the third derivative is something you just leave out. So you truncate it. So that means that the delta t cubed, that's your error. So your error goes like delta t cubed. So everything is just manipulations of Taylor expansions, all these methods. And if you think of what you see here, that's an industry standard. And then I was very surprised when I realized that. It's always a kind of balance between simplicity, accuracy, and the number of cycles you want to include. Now, so what you do then, if you look at this v of I, this second derivative, you approximate that one with Euler's formula, which says that we take the first derivative plus 1 minus v of I divided by delta t. And that is equal to the acceleration of a of I plus 1 minus the acceleration a of I divided by delta t. And then you plug that back again, this equation here, you put it back in here again. You have a delta t squared, which now has a delta t in the denominator here. So when you put it back, what you're going to get then is a v of I plus 1, which is now v of I. And now we're putting away the approximation sign. So we have a delta t multiplied with the acceleration a of I. And then I have plus a delta t divided by 2. And then I have a of I plus 1 minus a of I. And when I collect all terms, this gives me v of I plus 1, which is equal to v of I plus delta t divided by 2. And then I have a of I plus 1 plus a of I, because I have a minus here and I have a plus here. Minus ai divided by 2 in delta t and I have a plus delta t times A of I here. And then I have the expression for x of I plus 1, which is now x of I plus delta t multiplied with v of I plus delta t squared divided by 2 times A of I. And the error or truncation which we make the error which we have made now by these approximations goes like delta t cubed. So that means terms with the third derivative and higher. And this method here, which you see now, that requires that you actually calculate the acceleration twice. So you need first to calculate, need to find AI to get xi plus 1. And this equation, this method applies only if the acceleration A of I depends only on x. So when I have x of I can then feed in x plus I1. I can feed in that one and calculate A of I plus 1. And then I can calculate V of I plus 1. So if you now think of what you have done till now, if you look back at the gravitational force has an acceleration which depends only on position. So if your force has a dependence on velocity as well, you cannot use this method. So this is a method which is extremely useful if you have problems where you have a potential energy which depends only on the coordinates, which then gives you also force which depends only on the coordinates. And it is, if you're simulating materials, people are looking at phase transitions, you're running big systems with billions of molecules and atoms, this is actually the method of choice. So if somebody's interested in this kind of research in solid state physics and condensed matter physics, there are actually people at the physics department who deal with these kind of methods. And then you need a kind of potential which acts between the particles. And from that you can find the force. And then you can solve Newton's equations for many particles. And that's called molecular dynamics. And then this is actually the method of choice. So you see, I wanted to demystify many of these numerical methods, but because it's important that you see how they're derived, but you also see their limitations. And we as physicists, astronomers, and so on, we are the guys who are actually going to develop the next generation of algorithms applied to physical systems. And that means that we have to know what is behind the black boxes. And that's much more fun than actually just using a black box, right? So we have to understand the limitations. And we have to couple the limitations with our physics understanding. So if you have a problem where you have energy conserving forces, this is a typical method which you would use. If you don't want to waste time on that one and you just want to have something which conserves energy, Euler-Kroner saves the day. And you will play around a little bit with this in the midterm which we have now. So which contains a little bit about harmonic oscillations. And there are some numerical elements and things which you have seen before. And on Wednesday, I wanted to say a little bit more about harmonic oscillations so that we have the kind of theory which is needed for the midterm. And then on Friday, we just keep solving the midterm. And we do the same thing next Wednesday and Friday as well. So we're not going to have too much new material before we can tackle the midterm. Now, feel free to take a look at the midterm, and guys, don't hesitate to ask questions. I was able to actually speak today. I was surprised because when I began the lecture here, I just wanted to give up. Anyway, thanks for coming. Been a great pleasure to see you all again. Take care, guys. And feel free to ask questions, and hang around if you want to.